Good morning. This is Tim Stewart. I am president at Visual Decisions, and we're here today to talk about improving OEE with Industry 4.0 and operational excellence. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements, such as 30% increases in OEE, 50% scrap reductions, and much more. But Industry 4.0 alone won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of the new capabilities to drive real improvements. And that's why we have a unique approach to work with our customers to adapt processes to take advantage of the new capabilities and help establish a true data-driven manufacturing culture. So let's get into it. How can Smart and Lean improve your OEE? And first of all, what do we mean by smart manufacturing? On the right side is a graphic from the World Economic Forum. I won't go into all the details there, but Industry 4.0 encompasses a lot of different technologies. Some of the relevant ones I've pulled out on the left side over here, and the real focus for today is going to be on the top four of those, with advanced analytics, IoT, machine learning and AI, and augmented reality. But those technologies alone are not enough. I wish they were. The analogy I use all the time is a Fitbit. I bought a Fitbit 8 years ago, and I've been wearing it ever since then, and I've gained, unfortunately, about 20 pounds over those 8 years. And it's not the Fitbit's fault. The Fitbit works great. It's a perfect example of an IoT device. It has really advanced sensors. It collects information from your wrist, pushes that information to the cloud, has machine learning and analytics up in the cloud to turn all those raw signals into footsteps and heartbeats and everything else. And then provides a nice graphical interface, both on your mobile device as well as through the web and so forth. And unfortunately, even though the Fitbit itself works perfectly and the IoT is working as it should, because I haven't changed my behaviors, I haven't lost the weight. And it's the exact same thing with implementing these technologies on the shop floor. You can put all the advanced detection systems out there, all the advanced sensors, push that information to a cloud-based application, run advanced analytics on it and so forth, present that information very nicely to your people and so forth. But unless they do something differently tomorrow than they do today, you're not going to see the gains that you're hoping for. So you have to create that culture. You have to adapt your processes in order to take advantage of those new capabilities. So what we have done with our customers is to really combine the smart factory with these advanced capabilities and the lean factory that already has the tools in place to improve the process. But we can make those tools significantly better by utilizing the Industry 4.0 capabilities. So I'm going to start on the technology side and work my way towards the lean factory. So the first question is, where do we get the data? And how do we get comprehensive information about the process in order to improve it? So if I look and ask the question of where is the manufacturing data today, there is an absolute ton of data that you already have about your process, whether you've implemented IoT systems or anything else. There's a ton of data out there. You just may not be collecting it, storing it, and utilizing it. And so if we look at the devices and sensors, the controllers for your machines and so forth, will have data that gets wiped out every hour or every shift, every day, whatever it might be. You have different testing systems and everything else. And whether you're capturing that data or not, it is being generated. And so there's a lot of data out there. Then you might have, within your plants and operations, MES systems, LIMS, laboratory information management systems. You might have maintenance management, all kinds of different systems within the factory itself, operational technologies, basically. And then you might have additional things like video, surveillance cameras and so forth. You might have, different spreadsheets and access databases and everything else that you utilize today. And then if you make your way out into the supply chain and marketing and CRM and even out in the public and so forth, there's a variety of different information that will help to contextualize the information within the facility, plus a lot of very relevant information about the suppliers, the lots that they're shipping, when things are due in the plant, consumption rates at my customers, warranty information, field service information, usage information, telematics coming in from the products themselves and so forth, that can help give you information about what was done well, what wasn't done well on the shop floor once I start to draw those correlations. And so when I look at that raw machine data, what I really want to do is, instead of just trying to analyze that raw machine data on its own, I want to contextualize that information and look at that data within the whole framework of how that product, the material, the machine is being used, who was operating the equipment that day, what products were being manufactured, et cetera. And that's going to help me really utilize that information much more effectively. And so being able to look at not just the raw data itself in an island, through what you would normally see in like a data historian, just pulling raw information from the machine and just storing that, but really looking at the complete picture of if I see that the machine went down, what does that actually cost me? Who was at the machine at that time? Did I have the operator just standing there and I'm paying for his labor to do nothing? Am I having additional maintenance people come over? All of those different things can impact the cost of downtime. But unless I'm tracking those external factors as well, then I really don't have an understanding of that true cost that's associated with that machine not being available. The other high-level thing, one other high-level thing that we should look at here is that the metrics that you're collecting should really align to the different processes that you have in place. And so if you have a TPM, total productive maintenance process in place, and you're looking at, how can I improve my autonomous maintenance, my planned maintenance, et cetera, then, what is the information that I can collect from the process and, feed back to the operators, the maintenance people and so forth, that are going to help them optimize those activities. And so when I look at that later on, when we get to the section on those actual processes, what we should have thought through in advance is, what is the information that we need for that? What are we actually going to do in autonomous maintenance? And can we prompt the operator with information about, it's been X number of cycles since the last time that the oil was cycled, and we need to do that. This tooling needs to be changed out because it's reached the end of its useful life, et cetera. And so there's a lot of things that we can do, but we need to think through what are the different improvement processes that we have in place around, whether it's Lean or Six Sigma, TPM, total quality management, OEE focus, and things like that, and really collect the information that's going to be relevant to those processes so that we can make the improvements that we're hoping for. One other high-level comment on this is that collecting information at a performance level is very helpful, but it doesn't get you to where you need to be. So if I know that my first pass yield went from 97% to 93%, I know that I have a problem, but I don't know why. It's like your kid bringing home a report card at the end of the semester saying that they got a D in math. Well, okay, but how did that happen? And what were the drivers behind that? Did they not do the homework? Did they fail one test really badly? Did they do poorly on all the different tests? Because there are different things that you have to do to correct that situation based on what actually happened. And it's the exact same thing on the shop floor. You want to be able to look at not only the fact that I had downtime or I had a quality issue. I really want to track as much information as I can about why I had that downtime, what was the nature of the quality issue, and what drove that, and so forth. And by tracking that information, now when I go to improve the process, if I look at a Kaizen process, the first step is to collect data about, what are the things that are causing the problem that, I'm trying to address. And if I've done that, all along, then when I start that improvement process, I have a jump start on, having all the relevant information that I need in order to improve that process. One more thing that I'll emphasize very heavily is that you want to be able to dollarize all of this as much as you possibly can. You want to be able to associate dollars, with all of these different events happening on the shop floor. So whether it's a downtime event or whether it's a quality event, et cetera, I want to be able to track for, rework. Exactly how much rework did that take? How much capacity did I utilize on the machines in order to do that rework? Who was involved in that process, not just from doing the rework itself, but any material handling people, any engineering staff, et cetera, that had to get involved with that. I want to be able to actually monetize that entire non-conforming material process. And to do that, I really need to capture the details of what's happening on the shop floor. So when I talk to a lot of people about implementing OEE systems or I-IoT systems on the shop floor, what they look at is, just collecting information about the critical asset itself. And, that is the real focus of, the OEE specific applications, is that, they really want to focus on what is the downtime on that machine and how do I prevent it? And that's very important. But what that doesn't give you is that contextualization of what does that downtime actually cost you on that machine versus a different machine, if different types of downtime have different costs that are associated with them, and how much this is really costing the business in terms of the downtime here versus the downtime here versus these quality losses versus anything else that's happening within the facility. So how I optimize my time in terms of being able to address these issues, what I put at the top of the queue for the places where I want my engineering staff or my continuous improvement staff or my maintenance team to invest their time, should be driven by how much of an impact that actually has to the bottom line of the business. One more high-level thing about the data itself is that it can be very difficult for people that are involved in this process to be able to tell you this information about what actually happened, to be able to run those diagnostics and so forth. And so one of the things that you can apply the machine learning and the artificial intelligence to is not only being able to predict that, hey, my machine is probably going to go down with an 80% probability over the next hour. That's extremely valuable, but it's also very useful for doing things like automatically classifying the types of failures that I might be seeing or that have already occurred. And so by running classifier algorithms, I can automatically tag different events of downtime or different quality issues and so forth based on what was happening within the machine before those different events happened. And this can significantly improve the quality of my data and that contextualization of everything that we talked about, and having true actionable metrics that I can go and now address with my continuous improvement process. So it's not just collecting the data and running an algorithm to be able to predict when the next downtime is going to occur. It's also collecting that data and being able to interpret that data more efficiently and more effectively by utilizing some of these advanced techniques. The final step, that I'll emphasize once again, is that it's not enough to just collect the data. If it was, I'd be a lot thinner by now. In addition to wearing the Fitbit, you actually have to exercise and improve your diet. And again, it's the same thing on the shop floor. It's not enough to just collect the data and stuff it into a database and have pretty charts and graphs. People actually have to change their behaviors based upon the information that's in there. And so what we're going to talk about next is how to utilize all this information that we just talked about collecting to actually now eliminate or mitigate those losses. And so if we're talking OEE, and that is the subject for today, typically this is broken down into the big 6 losses. And from an availability perspective, that usually gets broken down into major breakdowns and then setup and adjustments. The performance losses gets broken down into the short stops. So anything underneath the threshold where I'm going to tag that as a major breakdown, and reduced speed where someone's running, a line or a machine at 100 pieces per hour when it's rated to run at 150. And then from a quality perspective, that usually gets broken down into, startup rejects versus production rejects. And so a lot of the attention, within this process gets focused on the breakdowns. And, I'll spend a lot of time there today as well to talk about how you can reduce the availability losses, because very often those are, the biggest drivers of OEE loss that you have. But I'll actually include these short stops right with those major breakdowns as well, because very often this is, the hidden factory. I've seen companies where up to half of their overall OEE losses were due to these performance losses of the micro stops. This happens very frequently where you have like packaging lines, and you just have continuous jams throughout the day, or something stops because the feeder got empty and so forth, and it doesn't take long to clear it, and nobody bothers to record that downtime because, hey, it only took 45 seconds to clear. But rather than just accepting that that's the way that the line works, if you can, identify those, maybe run the automatic classification on what happened, as opposed to having somebody, tag the fact that, hey, it was down for 30 seconds because of this, then you can start to look at exactly how much time you're losing due to these different issues. And often those, brief but frequent stops will add up to be much bigger than some of these major breakdown issues. And by addressing those, you can, significantly improve the performance of the line. And I'll give some examples of that later. So from, a resource availability issue, there's machine breakdowns, maintenance related issues, there's setups and changeovers, there's process failures where, I'm either blocking or starving the asset, or, I have meetings, or, whatever it might be. Then there's manpower issues and material issues that can, stop that machine as well. So if I look at, how I typically go about improving the process, that is done within a lean framework of, a Kaizen process, continuous improvement event. And if you look at how these are run, this is a, example of a 6-step cycle for Kaizen, but, there's different definitions out there, different steps that you go through, but essentially it's all the same. You're identifying problems, you're analyzing the reasons for those, you're brainstorming different solutions, and then going through a selection process. You're testing that out. You're measuring and analyzing those results, and then you're standardizing that solution across, the different shifts and everything else within that, individual process. But then hopefully also saying, what are we learning from this that we can apply elsewhere? And so, every single step in this process can be improved utilizing information. Certainly identifying the problems. We talked earlier about being able to dollarize, the different things that are happening within the plant, and really being able to prioritize, what are the problems that we want to address first. Analyzing the current process, all that we talked about collecting all of that data and so forth, and being able to look at the causal factors behind all of that means that I don't have to spend the first 4 weeks of my Kaizen event out there with a clipboard and a stopwatch to track what are the different reasons why the line is stopping. And then creating the solutions, you have a much broader solution set with all of these additional capabilities that Industry 4.0 brings. Testing and measuring and analyzing and so forth is all significantly improved. And so, your basic, most fundamental way of improving the process is significantly enhanced if you blend in this Industry 4.0 data, this I-IoT data, within that process, and you really train your people on how to utilize that information effectively. I promised to talk about maintenance earlier, and here it is. So, how do companies keep their equipment running? The maintenance practices can be broken down into a lot of different categories, but I've chosen 4 here. There's autonomous maintenance, where these are the day-to-day tasks that the operators themselves do to keep the equipment operating effectively. There's preventive maintenance that is more typically done by the maintenance staff, but are scheduled events based on either time, duration, or number of pieces produced, or something along those lines that says after X amount of time, I'm going to do this task. And then there's condition-based maintenance, which says, if my oil temperature exceeds this threshold, then I need to shut the machine down and either change out the oil or look at why that oil temperature rose. And then there's predictive maintenance, which takes that next step beyond condition-based maintenance and says, instead of just looking at simple thresholds, I'm going to run a model that looks at a lot of different criteria and actually comes up with a probability of failure based upon all of that different information. And then certainly keeping equipment running, you can do a Kaizen event. You can look at failure modes and effects analysis, running an FMEA on that process, and looking at all of the different potential failure modes and how you might address those and so forth. So looking at each one of those in turn, from an autonomous maintenance perspective, how do we give the operator the information that they need to very rapidly do what needs to be done, and honestly, and no more than that? So we can automatically track, the counts for, hits or pieces or, whatever it might be, and pop up, a list at the beginning of the day to tell the operator, here are the different things that you need to do today to, keep the machine running, and make that as easy as possible for the operator, not only by prompting them that it needs to happen, but also tracking the fact that it did happen, as well as giving them work instructions for how to do it and so forth. And those can be done either through a simple screen or whatever. You can also utilize something like augmented reality to make that very easy for them, so that they can actually kind of see the work instructions on the equipment itself, and make that perform those tasks much more reliably. And furthermore, we can optimize that maintenance schedule so that rather than doing things X number of pieces or X number of days, we can really look at the data and let the data tell us what that frequency needs to be. Along those same lines, preventive maintenance tasks are essentially bigger versions of those same autonomous maintenance tasks. And so the same things that we're doing with those autonomous maintenance tasks, we can do for the PMs as well. We can, automate the scheduling of those. We can optimize that schedule based on, the performance of the machine. We can look at, the work instructions themselves to make sure that things are being done correctly, and do everything that we can utilizing those augmented reality capabilities to kind of error-proof that process as well. Condition-based maintenance is really where the power of the I-IoT system comes in, and the ability to collect that detailed tag data coming from the controllers, and being able to look at the limits that you want to set on those different variables, and alert based upon those different conditions. So whether that's a temperature or vibration or power draw or anything else, pressures, etc., you can set those thresholds, or you can automatically adapt those thresholds based on the amount of variance that you see as you're running different types of materials and so forth. And so the machine itself can essentially tell you when maintenance needs to be performed, when things are operating outside of normal conditions. And so the condition-based maintenance, has a lot of possibilities with those IoT systems to really optimize that process, eliminate a lot of the PM tasks that are done on a timed basis, and move those to condition-based so that they only need to be done when they're actually required. From a predictive maintenance capability, that's really, again, kind of taking that condition-based maintenance with, pulling that IoT data, and now putting that into a model that allows me to not just look at one particular variable at a time and saying, is it inside or outside of a threshold, but really looking at a variety of different elements of that information at one time, and running that through pattern recognition to be able to identify where we see things similar to what's happened in the past that tells me that a particular failure mode is going to occur. And so the real difference between predictive and condition-based with these tools is that sophistication of the model. Rather than looking at one thing at a time with simple thresholds, I'm actually running that through the pattern recognition that's looking at multiple things at one time, and how those move together to generate that prediction of probability of failure. So those are a lot of different ways that we can keep the machine running. But no matter how well we automate those processes, we're still going to have breakdowns. So I've done everything I can to improve my mean time between failure. How do I improve my mean time to repair when the machine does go down? Well, if I look at the different components of responding to a downtime, the first thing that happens after the failure occurs is the operator has to be aware that the failure has occurred. And if the operator's standing right there, I've got a machine and an operator, as one unit, then they're going to know right away that, hey, the machine stopped. But if I've got that operator in a work cell where they're running multiple pieces of equipment, or a line where they're responsible for keeping that entire line functioning, if my filler stops and I'm down at the cartoning process reloading boxes, then I may not know right away that my filler stopped. And very often the filler is the constraining asset, piece of equipment within that line. And so when the filler stops, I'm losing overall capacity for that line. And so it's critical that that operator is made aware as rapidly as possible that, hey, I have a problem. And that could be done through something as simple as a traditional and-on light and so forth. But it should be done so that the operator is aware right away. The next step is for the operator to be able to triage that event. If it's a jam and they can poke it with a broomstick, then hey, they don't need any help. They can just clear the jam and move on. But at some point, the operator has to be able to know this is a type of failure that I can't do anything about, and I need help. So then they have to have an efficient way of notifying maintenance or engineering that the machine is down and they need assistance. And ideally, this is some idea of what the problem is. And once maintenance and engineering becomes aware, then somebody gets assigned to the problem. That person has to become available if they're in the process of doing something else. Then they have to travel to the machine. So then finally you have maintenance, arrive at the machine. Then they have to diagnose the issue and, figure out more of, a formal root cause analysis to understand, what caused that machine to stop. Then they have to fix the problem. And hopefully the problem is fixed at that point. Or you'll have to try again later because maybe they didn't have the right tooling, maybe it wasn't the right person to address that issue, and so forth. And so there are a lot of different things that can be done to improve this whole process, utilizing these different techniques. And so at the very beginning of this process, making the operator aware, that can be done again through something as simple as an and-on light, but you can text people, you can basically do anything that you want, utilizing these different technologies. As soon as that IoT system recognizes the fact that the machine has stopped, it can take whatever steps you want it to in order to make people aware that something has happened. The next step of the operator knowing that they need help. Well, very often that's kind of self-evident, but we talked about those classifier systems earlier, and being able to automatically identify, what is the nature of the problem. And so rather than having the operator do triage, we can actually have the system itself let the operator know, hey, this is a typical known type of failure. You're able to take care of this, poke it with a broom, versus this is something where the motor stopped and we need to get a mechanical person from maintenance involved. And so, a lot of that triage can be, automated so that it doesn't take time in this process. The next step of making maintenance or engineering aware. If we're doing that triage automatically, we can also tie that system into our maintenance system so that we can automatically create a ticket within that maintenance system that not only says, hey, this machine is down, go fix it, but also supplies that triage information that, this looks like it's a mechanical problem with the motor, and any additional context that can be provided. That way, when somebody gets assigned, we can have a pretty good idea that the right person is going to be assigned. A lot of maintenance departments are broken out into electrical versus mechanical and so forth, and being able to get the right person at the equipment in the first place is often, one source of extending that mean time to repair. So if we can get the right person assigned in the first place, then that can, certainly dramatically help. Being able to look at who's available in real time, if we have, good understanding of where all those people are, what tasks they're assigned to, how long those tasks are expected to take, then we can look at who's the next qualified person that will be available and get that person assigned to it so that they can get to the machine as rapidly as possible. And then, that travel time to the machine is kind of the travel time to the machine. Unfortunately, we haven't advanced to the point where we can, get that person there by transport or teleportation. Diagnosing the issue for the maintenance person. Again, if we can automate that triage process, that amount of time can be significantly reduced. And if we can let them know what that problem is in advance, they're much more likely to be able to fix that issue. The other thing is, if we're triaging that issue automatically and we have a database of what's been done about these issues in the past, we can, pop up information about when this failure has occurred. Here are all the different things that have been done to address this and how well they've worked. And so there are a lot of different things that we can do to provide that maintenance person with a lot of different information about how to fix these issues, what should be done, and what, how effective that has been in the past. All of which, as I've gone through this, will help us get it fixed on the first try as well. So one thing that can really extend our mean time to repairs, our first time fix rate. If our first time fix rate is low, our mean time to repair is going to be high. There's a definite inverse relationship there. And so, if we look at why the team doesn't get it fixed on the first try, it could be that the wrong repairman was sent. They couldn't diagnose the issue on the first try, on their own. They might not have had the required parts in stock. And they might have to leave the machine to go get the parts from stock, need different tools, need additional assistance, don't know how to make the repair. All of these things can be addressed with intelligent systems. I've talked about several of them already, but in terms of having the required parts in stock, if I'm running a predictive system and I have some idea of what types of failures are going to be happening over the next 7 to 10 days, I can make sure that I have spares in stock that are going to help me address those different issues. Having to leave the machine to get parts from stock, if I have people that distribute materials within my plant, if I have good communication mechanisms in place, when that triage occurs automatically in the first place, I can either have the maintenance person go to the storeroom to get those spares that are going to be required, or I can have a separate person meet the maintenance person at the machine with those spares in hand. Same thing with the tools. I can make sure that when the person goes out to the machine in the first place, they have a good understanding of what that failure is likely to be, and therefore can bring the right tools. If they need additional assistance, they need a call from engineering or something like that, using augmented reality technologies, instead of having to wait for engineering to come out to the machine, you can initiate an augmented reality call where you can actually utilize your phone to show what's happening within the equipment, get that feedback from engineering right there, like a really advanced FaceTime session kind of a thing. And not knowing how to make the repair, if this is something that's been done before, we can capture those work instructions and either have those on a traditional format on a computer or a phone or something like that, or go the augmented reality route and have that be much more sophisticated. But either way, we can provide a lot more information than has happened in the past. So that kind of addresses our mean time between failure, our mean time to repair, and our first time fix rate, and shows how we can dramatically improve each and every single one of those, utilizing these technologies when I combine them with those improvement processes. So setups are another big issue for a lot of different companies. And I'm not going to get as far into depth here, but certainly from a task tracking perspective, there's a lot that can be done these days with video analysis or doing automated spaghetti mapping, utilizing RFID chips and so forth. Looking at comparative analysis, if I'm tracking these things in detail, I can see which operators are doing a better job than other operators. I can see, for different products, if I have kind of a dependency between what product I'm changing from and which one I'm changing to, kind of like if I'm changing colors and paints, I always want to go from lighter to darker instead of darker to lighter, because the setup time is just, or the changeover time in that case, is just less before I have to do a complete washout. Visibility for advanced kitting, again, having those kits be put in place and brought to the machine in advance of when that setup is going to need to occur so that I have everything I need in order to do that setup very rapidly. And then just having the standard work, being able to capture that, being able to make that visible to people, and then tracking any deviations from that standard work so that I can see where I'm losing time and be able to avoid that in the future. So process failures, blocking and starving, different tooling issues, scheduling and coordination, lack of staffing, things like that. A lot of this is due to kind of issues with my plan that I have in place, or executing against that plan. And that's something I've done a recent webinar on, so I'm not going to get into a lot of detail about that today. But if I'm putting a great plan in place because I've collected the right information, I have all of the right conditions, I have the right times and everything else, my planning system has a much better chance of putting the right things at the right place at the right time. And then if I'm able to execute against that, replan rapidly, and detect any deviations from the plan and then adjust accordingly, I'm a lot less likely to block or starve different assets. So if we look at the performance side of the equation, pretty much everything that I've talked about with the major stops applies to the micro stops as well, but really even more so, because when I look at these things, the micro stops really go unaddressed today. Everyone knows they happen, but there's a mindset that that's just the way the line works. And so by being able to capture those, kind of automatically classify them, I can certainly get the flashlight shined upon those so that I understand what are those things that are driving my performance, and being able to get those addressed. And a lot of the things that you can do here are kind of manpower related. A lot of that, those stops are due to standard work not being followed. And again, being able to document that, make that available to people, and track any deviations from that is going to help me with, this person runs the line at this speed because they think it runs better, versus this person who cranks it way up and lives with some additional downtime. Well, who's right, and what is the right way to run that machine? What are the proper settings, and so forth? And so all of those different things can be tracked and identified, best practices, and monitored. And then training and error proofing as well can be really enhanced with all of this information. From preventing different causes of variation, if we look at manpower, running low on time, so I'm going to go fast. These are often the largest sources of variation within the process is the people. So if you look at why are the most common human errors happening, how often are those mistakes made due to lack of knowledge or experience? If I look at the variability that I have when new workers come on board and so forth, if I have a wide variance between different operators, then if I take all of those different sources of variation and I put good training programs in place, utilizing the information, I track the performance of different people in different ways, and don't utilize that to beat people up, but utilize that as training opportunities, I can significantly improve the performance of my people, as well as just tracking deviations from the standard work and things like that. And so I can reduce a lot of that variation by having these systems in place, helping to helping my people be as good as they can be within that process. Causes of variation in the machine. Six Sigma. So if I look at that machine performance, and a lot of the Six Sigma capabilities are based on data, being able to run those design of experiments and identify what are the different factors that are impacting my performance and so forth. All of those are based on data, and usually I don't have a whole lot of pushback about the fact that if we collect the more detailed data and be able to make that available to those Six Sigma improvement processes, that I'm going to be able to make a big impact on the process. From a method perspective, being able to get those standard operating procedures, get those the standard work defined, and be able to track the deviations from the standard work, being able to optimize what those standard operating procedures should be in the first place, that should all be based on the data, and being able to have the data out there and analyzed so that I can base my standard work and my operating procedures on that is something that should be relatively self-evident, that those can be made better if they're based on the actual data from the process rather than how I think things work. And again, being able to track deviations to all of those things in real time so that, things don't always go according to plan, but how rapidly can you identify that they've deviated from that plan and make quick adjustments is really a big part of the key to eliminating a lot of that variability, or at least mitigating or minimizing that variability. I don't have a lot of time left, so I'm going to go through some examples real fast. At a customer, bread manufacturer, we put a system in place that utilized the information that was already out there in the controllers and so forth. We just made it more visible and put it into a database and analyzed it over time. And being able to drill down into that information, we saw that the equipment loss was the biggest driver. When we click on that equipment loss, we saw that the oven within the equipment loss was the biggest source of downtime. And then if we looked at the cause, it was other, but we got people to put in good comments around that. And we saw that the oven shelves were flipping due to broken pins, and we were able to very rapidly identify that the reason for that was that they were getting fatigued as they were going through the oven, out of the oven, into the oven, out of the oven, and so forth. And so we were able to put a PM process in place to swap out those pins on a periodic basis, and eliminated the biggest source of downtime in the facility, really because we were able to get the visibility that that was the problem in the first place, and how much time we were losing justified that PM process. Then I have another customer where we're going through and optimizing how often we replace the tooling. They were spending a very large amount of money on grinding wheels on an annual basis. And part of that was that if they leave the grinding wheel on too long, it burns the part as the surface wears on that grinding wheel. And so what we were able to do is put a predictive process in place that looked at the remaining life on that grinding wheel. And that actually helped across all three phases of this. It helped reduce the downtime for failures, as well as how frequently those wheels needed to be changed. It helped quality because we burned fewer parts, and also just from a performance perspective, they had more confidence to run that machine at speed. They had more confidence where they weren't taking it down and checking the wheel periodically with short stops in the process that impacted the performance. So this one change really helped the availability, the performance, and the quality of that process. So with that, I want to thank you for your attendance today. And if you have questions, please let me know. Reach out to me either at my email or my phone number here. And I look forward to following up with you and talking more about how all of this can be done at your facilities. Thank you very much.